Hi, this is Abhilash Majumdar, a research scientist for Morgan Stanley. Previously, I was working with HSBC on NLP engineering, and I have also collaborated with Google Research on their language models, namely BERT, Albert, and happen to maintain some of them. I have been mentoring professionals and students on AI, NLP, and deep learning for organizations like Udacity, Udemy, Upgrad, and have quite considerable experience regarding this mentorship roles. Welcome to Co-Learning Lounge YouTube channel. As you might know, we have a series of YouTube videos related to NLP, starting from the basics to generic architectures of LSTM to state-of-the-art BERT models and attention. In this context, we are going to cover GPT, that is generative pre-training, generally 2, the second version we are going to cover because that paved the way for all the recent transformer developments, as well as GPT-2 is one of the most standard state-of-the-art architecture for generative modeling using transformers. So, and in the future videos, there will also be links in the description below. There is also a video related to the output of GPT-3, how it can be used for question answering or sequence modification, any NLP tasks in general. And you can visit that in Core Learning Lounge's YouTube channel. The link is provided. You will find it in the on the screen as well as in the description. So before we start with GPT-2, the most important thing is that we had studied about BERT, and in BERT, we had already seen how bidirectional encoder representations can be used to form it can be used for different language modification on language modeling tasks, let's say from NSP, next sequence prediction, to question answering, sequence classification, sentiment classification, abstractive text summarization. And we've also studied the core architectures behind BERT, how the standard encoder decoder architecture gets transformed into BERT architecture. What is the difference between a standard transformer to a BERT architecture? Moving along the same path, we are going to cover GPT-2. GPT-2 is a very beautiful architecture in the sense that GPT-2 does not have much of encoders. It relies mainly on decoders as its main structural framework. So GPT-2 generative pre-training 2 model is known as a transformer decoder because most of the architectures of GPT-2 rely on having efficient decoder networks. In the same context where we have taken the example of BERT and other transformer videos from Jay Alamar's blog post, we are going to take the same example over here. Now, the first important thing is understanding what is the difference between a BERT and a GPT. So BERT, which traditionally stands for bidirectional encoder representations, is kind of a discriminatory language model, discriminatory architecture, which involves both encoder and decoder networks. And we had also seen the importance of BERT in standard architectures, which had encoders and decoder representations, right? So inside the encoder, we had stacks of self-attention and multi-layered self-attention, multi-head self-attention, and we had feed-forward networks, we had normalization networks layers on top of each other. So encoders were there, and decoders also had the self-attention as well as the encoder-decoder attention and feed-forward neural networks. So this was what we had covered in the BERT. In the case of GPT, the encoders does not play a typical role here because the most of the hard work is done with the help of the decoder stack only. And there are certain differences between the encoder and the decoder stack. And before we go into the GPT variants, so GPT-2 has many variants, as you can see. GPT-2 small is there, medium, large, and GPT-2 extra large. But one of the major differences between the BERT and the GPT-2 model is that BERT has encoder-decoder representations, whereas GPT-2 stands for only decoder-decoder, multi-layered decoders on top of each other. It is generally known as a transformer decoder, right? So moving forward, one of the other important differences between BERT and GPT-2 is that, BERT, on the other hand, where we have GPT-2, is a transformer decoder block, as we mentioned. It also uses something called as, masking. So when we come to the comparison of attention layers or attention blocks, in the case of BERT, we have already seen self-attention, we have already seen multi-head attention. But in the case of GPT, we will find that it tries to mask the attention weights up till from the left-hand side to a certain point. Let's say we have only 4 words in a particular corpus, and you want to, and if the masking in GPT-2 is considered, then only, let's say our current head is on the 3rd word. So all the words from 0 to 3, that is 0, 1, 2, and 3, all of these words will be masked. All of these words will be present, and the rest on the other right-hand side will be masked. So this is one of the major differences between BERT and GPT. Whereas in the case of BERT, all of them are considered at the same time, all of the words that are present in a particular sentence or a particular corpus, and there may be self-attentions applied on it. But in the case of GPT-2, so there is a masked self-attention which is getting applied on it. So masked self-attention means that where the current head or where the current attention head is located from the starting, from the leftmost starting point to that particular head, all of them will be considered, while the rightmost parts of it, whatever is there, that will not be taken into consideration. And this is one of the major differences. One key difference between the two is that GPT, like the traditional language models, outputs one token at a time. Okay, this is another very important difference. As you can see in the example, this is a lighter difference because in the case of BERT, what we had done, we had taken the context from both the left hand side and from the right hand side, as we saw in the encoder representations, right? So encoder means bidirectional. There is a bidirectional concept applied to it. So both the left-hand side and the right-hand side of the context are taken while computing the self-attention and the multi-head attention weights. But in the case of GPT-2, we are only considering one side of it, and the other difference is that we are taking one output token at a time. So it is not that you're taking 2 3 4 tokens together and you are applying your self-attention mechanism, multi-head attention mechanism like that. Another difference is that these models, whatever we consider regarding GPT, like GPT variants, GPT-1, GPT-2, and even GPT-3, so these are kind of autoregressive models. The main part or the main working functionality of an autoregressive model is that when these models actually work, after each token is produced, that token is added to the sequence of inputs, and these sequence of inputs are fed to the these sequence of inputs are in turn fed to the next step, next layer, right? And in this way, this entire sequential process continues. Autoregressive models have the idea that when a token is getting output at a particular layer, whatever is getting output there, that becomes the sequence input to the next layer. And in the case of GPT, these layers are only comprising of decoder stacks one after the other. And as we know, in decoder stacks, we have the self-attention, we have the encoder-decoder attention, and we have feed-forward neural network. There may be add and normalize in between them, but these are the main important features of a particular GPT-2 model. In the case of BERT is not that kind of autoregressive model. So BERT, in losing its autoregression, gained the ability to incorporate context on both the left and the right hand sides of a particular word. As I mentioned, right, bidirectional encoder representations has encoder stacks, and in those encoder stacks, we have bidirectional LSTM stacks or GRU variants, anything. And that is where it gets to pick up both the left and right hand side of all the important features, all the important contexts. Right. So in GPT-2 and some later models like Transformer XL and XLNet, these are autoregressive. Autoregressive means that whatever output we are getting one at a time, whatever tokens we are getting one at a time for a particular output layer or particular layer, we are feeding that as sequence inputs to the next layer. The initial transformer paper had only these two blocks for a particular encoder block, but in the case of a GPT-2 there is no encoder block as such. So in this case we have only this particular layer, right? The GPT transformer has only the masked self-attention, the encoder decoder self-attention, and the feed-forward neural network. There may be layer normalizations in between them, but this is the core architecture. So just like I mentioned, the masked self-attention is very aptly denoted in this figure here, right? So in the case of normal self-attention, which is there in BERT, like these are added multiple times. If we recollect that in BERT base, we have 12 transformer blocks. That means 12 encoder stacks and 12 decoder stacks. So that becomes a multi-head attention, self-attention. In the case of GPT-2, we have masked self-attention. As you can see in the colored figure, so all the blocks from the left-hand side to where the current attention head is present, all of them are considered, whereas the right-hand side of it are not considered. And this is a major drawback in the case of GPT-2, as well as a major enhancement for functionality for BERT, because BERT takes into consideration both the left-hand side and the right-hand side context, as it is very clear in this figure. But in the case of GPT-2, we only see the left-hand side of it. And that is why it only outputs one token at a time as it reads the context vector from the left-hand side to the current context vector head, which is over here, right? And there is another difference which I mentioned, that it is only a decoder block. So decoder block also, it has certain advantages on its own, being it can be easily scaled. But on the other hand, due to the loss of encoder stack, there is some attention weights which are not getting collected. So in that case, these kinds of generative models or GPT variants are not well suited for any kind of classification or discriminatory tasks. In the normal cases of discriminatory analysis, where we want to have sentiment analysis, right, these kinds of architectures are not generally recommended because it fails to pick up the context vectors from both the left hand side and the right hand side of it. And on the similar benchmark model, benchmark data sets like Superglue, Glue, right, Squad, and all these kinds of things, you will be seeing that in the case of generative modeling or generative data sets, GPT performs way better than BERT and its variants. This is the reason, because GPT outputs one token at a time, and it takes into consideration from the leftmost to the current context vector. Whereas in the case of BERT, if you were to do generative modeling with BERT, that can also be done, but there will be a loss of efficiency because we need to consider both the left and right occurrences or left and right context vectors for BERT, for applying generative models with BERT. How were to apply generative models with BERT if we do not know the right hand side of a particular word, right hand side or right hand remaining sentence of a particular word, right? So in that case, BERT loses some advantage in the case of generative modeling. Whereas in the case of discriminatory modeling, like sentiment analysis and all these kinds of things, the GPT loses some performance. And we have already seen this is the typical architecture of a transformer decoder, which is the GPT-2 block, right? So there is another important in-depth analysis of GPT-2 which Jay has provided, and this is very good in the sense that in the case of standard BERT architecture, we had two tokens. One of them was called the CLS token, and one of them had the was called the SCP token. And that is CLS stood for the first or the starting point of a particular sentence or a corpus, while SCP stood for the end or the terminal point of a particular sentence of a corpus, right? In the case of GPT-2, we have the same methodology, but we have a start token and we have an end of text token, right? But GPT-2 is allowed to perform or ramble on its own, which is a major depiction of its generative modeling performance. Okay, as you can see, like in this case, in this particular GIF, only the word we have specified as input as the start token, right? And all of the words which will be getting generated after this will be generated by the decoder transformer, right? We will not be providing any context initially. We will just be providing a single word, that is the, and we will allow the GPT-2 to perform its prediction or its generated sampling of the next words or next corpuses or next sentences with its transformer decoder blocks. Another thing to note is that GPT-2 model is trained on large web text corpuses, right? They have crawled, the OpenAI people have crawled, thousands of web corpuses in their research, and they have applied all those research materials for the performance or evaluating the performance of this GPT-2 model. And in this way only the GPT-2 knows which prediction vector is going to come after which particular word or a sentence or groups of word like that, right? So GPT-2 has a parameter called as top k that we can use to have the model consider the sampling words other than the top words, right? In the case of top k, if we place it as 1, then what will happen? We will be considering only the words which are the topmost or the highly occurring words. Now what were to happen if we can change that top k? So we can also include other words which are there in a particular corpus, right? In the case of generative modeling or generative language modeling, this is really very, very important, because we need to have the correct context. Whatever the generations comes up, whatever generated sentence comes up, there should be a particular meaning to that particular sentence. Okay, now if I were to say in this example, the word which comes after the is thing, that means that one token at a time. That means the thing particular token or thing word, that particular word is getting output for a particular layer, right? And this particular token or this particular word which is named as thing, this is the input to the next stack, next input layer, right? So this is how the GPT performs. It takes one token at a time and it feeds it to the next layer, right? And each layer of GPT-2 has retained its own interpretation of the first token. Why? This is because we are feeding each token, each output token, to the next input vector. And we use it for multiple times for pre-processing the second token. Okay. Now, input encoding. A deeper look inside this particular GPT framework, we have the same input embedding tokens that we were using in all our architectures, right? The input remains the same as if it were BERT, standard transformer, or anything. So we have the standard input token embeddings, right? 768 in case of small, 1024 in case of medium, 1280 in case of large, and 1600 in case of extra large. Whereas in the case of BERT, we originally had two variants. One is the base, that is 768, and one is the large, that is 1024. Now we look up the embedding for the start token. Now compare this with the BERT, where we looked with the help of CLS token. Same here, we are replacing the CLS with the S token, right? Which is the start of the embedding matrix. Before handing to the first block, we need to incorporate certain positional encoding, right? Or positional encoding, this was also the same feature which was there in BERT as well, where we place position vectors for each word present in a particular corpus. So this part remains the same as BERT. What the difference comes here is in the architecture. So in case of BERT, we originally had an encoder stack before we moved on to the decoder stack. But what we have here, once we get the token embeddings, that means the input embeddings, we also get the positional embeddings. But what we get after here is the decoder stack or decoder transformer block only. And in this decoder, we already know there are self-attention blocks, there are encoder-decoder blocks, right? Encoder-decoder attention blocks, as well as FFN, feed-forward neural networks, which is a dense block. And this is provided in the figure here. And we have the masked self-attention, as we mentioned, which is one of the most important properties of GPT-2. So, so if we were to see what were to happen, so if we were to pass this particular S or the start embedding, we were to have after that a positional encoding, right? And what gets after that is the decoder blocks. So it gets passed to the self-attention, which is masked in nature in GPT-2. And we have the feed forward blocks, and this is first layer of decoder, and there are several layers of decoder one after the other. Okay, and we can concatenate these results at the output, and the output after this is fed to another feed forward or a final terminal dense layer, right? Now in this case, this particular architecture is very much different from BERT, and here is where the ability to predict what is the next word or what is the next sentence comes in, right? We are using generative modeling for this particular GPT-2 architecture, and we can see that how the mass attention works over here. A robot, right? Up till now, the current context vector is still here, that is it is the current context vector attention head. Okay, now all the words, that is a robot must obey the orders given, now these particular words from the left hand side, that is the start of the S token, towards the current context vector head, all of them will be considered, but the rest on the right hand side of it will not be considered. So taking this word, that is the it word, as the pivot, we are only considered what is on the leftmost parts of it. We are not considering what is the rightmost part of it. Why? Because GPT-2 functions in a different way. We are taking one token or one word at a time, and we are feeding it to the next input layer. So this is a token by token operation. And because each time we feed a new token one after the other, right, we are automatically changing the context vector rapidly. So in the case of BERT, where we almost had, for a particular layer, we had almost static context vectors because we're taking both the left hand side and the right hand side of it. Here, there is a little bit of a change. We are only taking one token at a time for each input layer, and that is where the context gets changed very rapidly. Okay, so in this case, this is what is mentioned in the paragraph over here. The self-attention layer in the top block is paying attention to a robot, right? When it processes the word it. And this vector will pass it to the neural network is a sum of the vectors for each of the three words multiplied by their attention scores. Okay. Now here, in case of the normal self-attention, which we computed in the case of BERT, the same thing is there, but we are not taking the rightmost parts of all of the words that are present on the rightmost parts of a particular pivot word. Okay. We are only taking the leftmost parts of it. Okay. And so the rest parts of it regarding self-attention is pretty much the same, where we have the Q, K, and V vectors, query, key, and value vectors, right? We multiply the input tokens or the input embedding with respect to Q to get the WQ value, right? Which we already had learned previously. We multiply the K with respect to the input embeddings to get the WK matrix, right? Similarly, what we do after that, we multiply the Q into K transpose. We take a square root of dk, right, which is the temperature in generally by the people of Google Research named it as temperature, which is generally root over 64, which is 8. And we take the softmax activation of it, and then we multiply it with the value vector, right? The value vector is again attained by multiplying v with respect to the input embeddings. So wv is present. So once we get that, right, we sum it right? And we get the Z vector. We have already studied it in the BERT model, right? When we are dealing with transformers. So self-attention remains the same, just masking is present, nothing else. So the two major differences in a particular GPT-2 block is that the first difference is in the architecture. In BERT, we had encoder blocks as well as decoder blocks, whereas in the case of a GPT-2 framework, there are transformer decoder blocks only. There are 4 variants of GPT-2, whereas there are 2 variants of BERT. And in the case of classical BERT models, we already had bidirectional representations. That means we are taking both the left hand side and the right hand side, tokens, context vectors for representing our word language model. But in the case of GPT-2, that changes. Why? Because we are feeding one token at a time to the next input layer, and this in turn changes whatever context we are taking. The second important thing is, in the case of BERT, we are only taking self-attention, normal self-attention, and since there are 12 transformer blocks, multi-head self-attention is there. In the case of BERT, in the case of GPT-2, the difference is that we are taking masked self-attention. That means whatever starts from the S token to the current context vector, we are taking that into consideration. Whatever comes to the right-hand side of it, we are leaving it out for the current context vector or the attention vector, right? So due to this masked self-attention, we only have that in the decoder stacks, and these decoder stacks are multiplied, let's say 12 times to get the transformer decoder architecture of GPT-2. And since GPT-2 only takes one token at a time, that is why it is very good for generative modeling. Whereas in the case of BERT, BERT generally uses both the left and right hand side of the context vectors. Hence, it is not suitable for generative modeling. Whereas BERT is very much good for sentiment analysis, discriminatory modeling, and everything related to discriminatory language modeling in general. So the second most important thing is GPT-2 always output token probabilities, right? Because after the decoder stack, we generally have a feed-forward neural network followed by a particular softmax activation, right? And this softmax activation generally outputs probabilities. So we get a probabilistic value of all the output words. This is how the general architecture of GPT-2 and the general functioning looks like. So we have the start token, we have the positional encodings, right? We pass it through the decoder stacks with mass self-attention in them, and we get the output. We multiply it with the token embeddings, right? And we pass it through a softmax. There should be a softmax activation to get the output probabilities or the logits generally, right? And once we get the output probabilities, we pick an output token based on its probability value. That is, it can be the maximum value generally, which is taken for our generative modeling. So we take the maximum output token value probability for our use case. So in that case, GPT-2 is generally a generative model, whereas BERT is a discriminatory model, right? GPT-2 architecture is different, and that is why it is called as transformer decoder models only. It has mass self-attention, right, which is another important feature. And since it processes each token by token, so that is why it is good for generative modeling, whereas BERT is good for discriminatory modeling, right? So this was all that is there in the case of current GPT-2. GPT-3 is built on the same particular aspect, and it is trained on billions of corpuses, and it has 175 billion parameters to be trained in GPT-3. So GPT and GPT-3, these are all generative samples, generative modeling, right? And they are used exceptionally, they perform exceptionally well when we want to generate something. So in this particular video on this YouTube by Co-Learning Lounge, which I mentioned at the start of this video. So here we can see OpenAI GPT-3's examples with the help of SQL, right? How we can generate them, how you can make the processing very much how GPT-3 actually generates these samples. So it is very interesting to observe them, right? And you will find that in the links in the description below, right? uh, you can also see how GPT-3 outperforms GPT-2 on major benchmarks, right? And since the development on transformers is continuing, right, as of this moment, so there are lots more things which are coming into place with the help of multimodal learning, where we are applying transformer models on both images and as well as words in general. So lots of things are happening. So stay tuned, and thanks for watching this video, and that will be all. Thank you.